Hey everybody, welcome back to our Common Filter Theory and Applications videos. This is the second playlist, Equation Drill Down, and now we're on the fifth video in the second playlist talking about the resistor. Now the resistor is something we looked at in the first playlist, but we dealt with it as a running average. In this one we're going to actually apply a Common filter to it. So if you recall, we have a very simple system. It's a resistor. There's only one state that we're interested in, the resistance. System dynamics is constant. There's no change in the resistance over time. And the measurement is of ohms from the voltmeter. So very simple. We have some measurement noise there. But we're going to have, for the moment, we're going to have no process noise. So phi is 1. Because it's constant dynamics. H is 1 because we're measuring the state directly. Q is 0 because we have no process noise. And R is sigma squared. So the state extrapolation and covariance extrapolation models are quite simple. Since there is no dynamics, whatever we came up with for the update at the last time step, that's what we're going to use as our prediction for the current time step. And the same is true of the covariance. Notice that the covariance is a scalar. The Common gain equation is quite simple. It's really a scalar ratio of P minus over the sum of P minus plus sigma squared, the measurement noise. The state update equation is also quite simple. We just take the predicted measurement, which is the same as what we had the last time around, and we add to that the Common gain times the residual. And the residual is quite simple because the H matrix is just the scalar 1, so the residual is just Z minus X, the predicted state. The covariance update is also simple. We just take 1 minus the Common gain, multiply it times the predicted covariance, which is the same as the updated covariance from the last state, and then that is our new updated covariance. So here's a plot from the Python simulation, which we'll take a look at in a second, for the Common filter resistor problem. When we compare that to the running average, you'll see it's almost identical. We get the same results. The running average didn't really care how big the measurement noise was. As long as it was zero mean, it averaged it out and converged. The Common filter knows what the variance is on the measurement noise, but it doesn't really matter because it's averaging it out as well. So the results are identical. Now the sawtooth plot is really just a stair step because there's no process noise and there's no dynamics. It's just constant dynamics. So there's no growth in uncertainty with the passing of time. But there is reduction in uncertainty as we take more and more samples, and so you'll see a stair step like this. Okay, now let's jump over to our code. Take a peek at the simulation. Okay. Going to the top of the file, you'll see that this is kfresistordemo.py. There are a number of imports, standard imports. The ones that are custom for my collection of Python scripts are this one that contains the moving average routines, plus it also contains the TME plot function. So you might want to look at that. And the last one, collate, is also one that prepares vectors for the sawtooth plots. So you can see here we're setting up the simulation with a number of samples. We got the truth model, we're calling it truthvec. We also call it x underscore true. X underscore hat is where we're going to be storing our estimates of the state. And then we have our phi, which is 1. Q is process noise. In the last run I included process noise, but for this one I'm going to change that to 0 so that we don't have any process noise at all. And then we have our initial covariance value and our measurement noise of 1 ohm squared. All right, then we set up some random noise that we can add into our truth vector to get our measurement model. That's this guy right here, the Z. And we'll set the initial value of our estimate equal to whatever the measurement was, just for simplicity's sake. The H matrix is 1, so the math will be simple, as we mentioned. Let's move on down. We've got some more initialization going on, and then we've got these two vectors, time series vectors, pre and post, which is where we're going to be storing the covariance value, both before update and after update. And that will be the basis for our sawtooth plots. And the Kalman cycle looks like this. We start at index 1 because index 0 is already set up with initial values, and you can see that the dynamics are implemented just as we talked about in the slide. After that, we set up some plots, and we call this function the TME plot right there with the associated parameters, and then we generate the sawtooth plot down here. So all very simple. Now let's look at those plots. We'll let me run this because I've got an older plot there. Let me run this, and now we'll look at the TME plot first. Let me go to a better view of the plots. Okay. So here you can see that we've got a TME plot which shows the measurements in red bouncing around the truth. The truth doesn't have any process noise in it because it's a straight flat line, and you can see that it converges just as we would expect the estimate. All right, and the sawtooth is very similar as well. It's got the stair step as we saw in the slides. Now let's go ahead and change the model a little bit. Let me go back and show you how I'm doing that. Turn off the spider plots, and we'll go up here back to the top where we had our process noise, and we'll make that into a fairly large value. We'll make it 4. So that's 2 ohms, or 4 ohms, 4 square ohms. Okay, let's save it. We'll run it, and then we'll go look at our plots. Okay, first of all, let's turn on the plot window. There you can see the the sawtooth plot is quite dramatic. It goes up very high because of the very large process noise. Gets an update, and because we have small measurement noise, R equals 1, it comes way back down, but then as time progresses again, it goes way back up again. So we're getting a very dramatic swing up and down in our covariance. If we look at the TME plot, you'll see that it bounces around. The estimate itself, it bounces around. It's not really converging very well because of the presence of process noise. So it's not very confident. Okay, I'll let you folks take a look at those scripts and play with them yourselves. And we'll go back here to the slide deck and finish up. All right, so where are we at? We reformulated the resistor model as a very simple Kalman filter. We've looked at the plots produced by the script, and we've seen that they are almost identical to the running average plots as long as we don't have any process noise. Then we added in some process noise and saw what effect that had on the plots. The stair step went away, and we had a real sawtooth plot with growth in covariance because of the presence of process noise, even though the measurement model and the measurements brought the uncertainty down. So what's next? Next video, we're going to look at an honest-to-goodness matrix model. We're going to look at a 2-state constant velocity system. So that's it for this video. We'll see you in the next.